Hello, I'm Tomáš Pevný, and I'm a researcher at AVAS and at Czech Technical University in Prague in the Artificial Intelligence Center. I will talk about hierarchical multi-instance learning and motivate my talk by a challenge hosted at Kaggle 2 years ago. The goal was to identify type of the device based on its network scan. And the challenge was interesting by the source of the data because they were not tabular, but they were JSONs. And JSONs can be small and they can be large, they can have some keys missing, and they can be enormous. And your classifier has to be able to deal with all these types of JSONs, ingest them, and ideally to use all the available information. And that's not trivial. So what are our options? So first of all, we can do feature engineering, and that was what the winner of the challenge did. The second is that we can take the JSONs and treat them as an image, and plenty of people do that, and as I will show you, it has some merit. The third approach is to take the JSON, strip the structural information, and treat them as a text, and then use some big natural language processing model. And finally, the approach that I advocate is to use the structure of the data and reflect the structure in the model. So let's look at the individual approaches one by one. I will skip the feature engineering because there is not much to automate and it's mostly based on the experience of the humans. So let's look at the JSON as an image approach. Here I took a first few samples from each class, and you can see that even though the approach is bizarre, the classes differ, or the images representing the samples from individual classes differ from each other, and therefore the convolutional neural networks will surely pick something and they will deliver some performance. An alternative is to treat JSON as a text by stripping the structural information, and surely NLP models will pick some statistical information and deliver some performance. And although you would need to deal with a difference in sizes of samples. But let's now look at the HML. The idea in HML is to take the structure of the samples and reflect that structure in the models. If you look carefully at JSONs, you will notice that there are three types of nodes. There are leaves, there are arrays, and then there are dictionaries. And the idea of HML is that for each type of the node, we design a model whose output will be a vector of a fixed dimension. If we create such a model for services, it needs to take as an input an array of arbitrary size, and as an output produce a vector of a fixed dimension. And the design contract that we use is that the model can assume that its child can be represented as a vectors of fixed dimension, and it will output a vector of a fixed dimension. And by the virtue of this recursion, you will be able to represent arbitrary JSONs. So let me demonstrate the idea. Let's first look at the leaves. Both can be treated as numbers and we can represent them just as a float. That means a vector of a dimension 1. The protocols can be treated as a categorical variables and we can represent them as a vector of dimension 2. So it's trivial. And similarly, there are a bunch of strings, and the strings can be represented by vectors of fixed dimension. For example, using n-grams or one-hot encoding or some clever byte pair encoding, etc. Well, then there are dictionaries. And to represent dictionaries as a vector of fixed dimension, it is sufficient to take the representation of their childs and concatenate them. So that's pretty trivial. And the real deal comes with arrays. The arrays can contain arbitrary number of items. We assume by the design contract that the items can be represented by a vector of a fixed dimension, but we need to output them as a vector of fixed dimension. So typically we use some element-wise reduction as a mean or maximum. So we do this for services, and we do this for MDNS services. And then there is one more topmost dictionary, and we again concatenate. And since at that moment the whole sample is represented as a vector of a fixed dimension, it's trivial to create a classifier into the desired number of classes. So where are the parameters? Well, the parameters are at the arrows, because each arrow can be replaced by a feed-forward neural network with arbitrary size and shape. And notice that we always use the same network to the same entity. So ports are processed by a feed-forward neural network F1. The protocols are always processed by network F2, their concatenation by network F3, and so on. And the whole scheme is designed such that it's differentiable, which means that you can take the gradient with respect to the network F9 and use that gradient to update the parameters of the network F1. We evaluated our solution on 3 datasets: mutagenesis, device ID, and Ember, differing in the size. From the prior art, we have selected the best models, and you can see their accuracy in the last column. The first column, denoted HML default, corresponds to the accuracy that you can get if you use the JSON Grinder library with defaults. The middle column, called HML tuned, corresponds to accuracy that you can get if you optimize hyperparameters. And that optimization can be on different levels. Sometimes it's sufficient to add more neurons, but for example in the Ember we had to use boosting. Well, the question that you should ask is that our solution is theoretically sound. We know that for feed-forward neural networks there is an approximation theorem. And that tells us that if you have a feed-forward neural network with one hidden layer and sufficient number of neurons, you can arbitrarily closely approximate any measurable function. So this is the famous theorem by Leshno from 1993. We wanted to have the same theorem for JSON structures. We have started by first extending the theorem to sets. Particularly, we have proven that any measurable function from a compact set of probability distributions to Euclidean spaces can be arbitrarily closely approximated by our construction, which uses two feed-forward neural networks F1 and F2, and in the middle of them they aggregate the results of the first one using mean. Then, by the virtue of recursion, we have extended the proof to a large class of structures that reflects the structures of JSONs. Let's now move to a concrete implementation in mil.jl. Mil encodes a structure of samples using nodes derived from an abstract node. For most problems, it's sufficient to use product node, bag node, and array nodes, but you are free to design your own. Each node has to have a corresponding model, and the goal of the model is to take an observation and project it to vectors, such that there will be one vector for each observation. I will demonstrate the library on this following small sample from device ID problem. Let's start with a representation of the leaves. For example, MAC address is represented as a string. Although you can represent the string as you wish, we generally use n-grams because we have an efficient implementation of matrix multiplication in n-gram matrix, and they are generally sufficient. You need to wrap the representation in array node to signal that there are no children. For the array node, we create a corresponding array model, and typically we just use layers provided by Flux, in this case a single dense layer, and applying the model on the node, we can see that it has been projected to a single vector. Let's now move to protocols. There has been 4 leaf nodes, and therefore we will represent them using a continuous array. That's because representing them as a structure of arrays is faster than arrays of structure. Since protocol has a low number of unique values, it makes sense to represent them using one-hot representation from Flux. And similarly, the model will be again just a simple dense layer as we have used previously. And we can see that now the model projects it into 4 vectors, since there are 4 observations. And the same goes with ports. In this case, we would represent them by a dense matrix for demonstration purposes, even though it doesn't make much semantic sense. You can see that everything goes as expected. Let's now move one level up. The port and protocols are a part of the arrays called parts of the services arrays. So first, we need to represent this array of dictionaries. So we first represent the dictionaries itself, and for that we use a product node which will contain a named tuple containing the childs. It would be protocolled and the port. Similarly, the product model will contain models that will process the childs, the protocol model and port model, and then one feed-forward network that will project their concatenated representation as ports. So finally, when we use this service model on services, we can see that it is still projected to 4 vectors. Let's now move again one level up. The services is an array, and that array corresponds to a single sample. In the design idea of mail, this array of 4 items is a single array, and therefore it needs to be projected to a single vector. To signal that in the mail, we create a backnode which will contain all dictionaries and signal that the array has 4 items. Corresponding backnode will contain model which will project the items, the one that we have defined above, and it will have an aggregation operator which aggregates arbitrary number of vectors to a single vector. We usually use mean and maximum simultaneously because we are never sure what is better, if mean or maximum. And then there would be one more model that will project the aggregated representation. So our back model would look like this, and if we apply it to a services, we can see that the array has now been projected to a single vector. To finish the representation of the sample, we will just wrap it in one more product node which will contain the array of services and the MAC address, and similarly we will create the model as we have already described above. You can see that right now we project to the desired number of classes, which is 13. As you can expect, we implement the interface common in the ecosystem. So you can concatenate the samples together. Notice that the leaves are represented as a continuous arrays for efficiency. You can estimate or you can get the number of observations in the dataset using knobs. You can index into the dataset as expected. Finally, if we apply the model on a dataset containing more observations, we get their projections. The library is of course well integrated with Flux, meaning that you can easily get parameters and you can easily take gradients. The above manual process is quite boring and it's also prone to errors. Particularly when you are designing models, it's quite tricky to get the dimensions right. Therefore, we have created one more library called JSON Grinder, which tries to simplify and automate the process. I will demonstrate JSON Grinder library on a device ID process again. I have loaded the data, extracted labels, and here you can see the first sample. Recall that the first thing we need to do is to take input JSONs and convert them to MIL structures. This can be very difficult, and therefore we want to create a function which will do it automatically for us. We will call this function extractor. To design this function, we need to know the schema of the data. Therefore, we have a function called schema, which estimates from a set of JSONs. You can see that the function didn't only estimate its schema, but it also calculated some summaries of values that can be found in lists. These summaries is very useful for deciding how to represent leaf values as vectors. You can create the extractor entirely by yourself. You can use prepared primitives, or you can do it automatically using the function suggest extractor. This is of course our preferred way. The function uses heuristics to decide how to represent the leaves. For example, the class ID has low number of unique values, and therefore it's represented by a categorical variable. Notice that there is an extra dimension, and the dimension is used to represent values that has not been encountered during creation of the schema. Contrary, notice that IP and MAC addresses has large number of unique values, and therefore they are representing using strings. Also notice that port has large number of unique values, and since it is a number, it's going to be represented as a float 32. You can argue that it doesn't make much sense, but it is a heuristic, and heuristics are not perfect. You are of course very welcome to tweak the heuristic according to your wishes. Now, if we use the extractor on a first sample, it is converted to MIL structures. Notice the special matrices called maybe something, and those matrices are used to deal with missing values, which are very frequent in JSONs. So once we have the extractor, we will use it on all data and convert them to MIL structures. This will naturally take some time. Once data are stored in MIL structures, we need to create a model. You can create the model entirely by hand, but it's much easier to use a reflect in model function which does it for you. It takes one sample to know the structure of the data, and a function which creates feed-forward networks inside the model. In this case, these feed-forward neural networks would contain just a single array with 32 neurons. It also needs a function which prescribes how to create aggregation functions. In this case, we will use min and maximum again. Reflect in model allows you to insert special feed-forward networks to any position inside the structure, but we rarely do that. We only use it to prescribe the dimension of the very last network, because that needs to be equal to the number of labels. You can see that creating the whole model is then piece of cake. Once the model is done, we proceed as usually. We split the available data into training and testing set, and we define the loss function. Before training, I will calculate the accuracy using this nice one-liner. You can see that the base accuracy is low, which is caused by having 13 classes. Now, we can use flux train function to train the model, which is going to take about 2.5 minutes. Once the training is done, we recalculate the accuracy again. Thanks to JSON Grinder, creating a classifier for a relatively complex data was a piece of cake, and most of the time it was mainly an automated process. As it is getting dark, let me finish. I think that our library works quite well as it is right now, but there are certainly things that we can improve. Personally, I would be interested with integration with geometric flux because it would enable us to model graphs where each node and edges would be described by JSONs. Other interesting integration might be with MLJ and EasyML. One thing that we are certainly missing is a neural architecture search, but I am not aware of any major Julia package. We are currently working on intramodel parallelism, since our model is a tree and tree can be easily parallelized. And finally, we are working on a module that would explain the decisions. So I will finish by encouraging you to try our libraries and report issues, and by thanking to my coworkers.